Correct. Okay, great. Well, good evening, everybody, and thank you very much for coming. Oh goodness, we have 286 people in the room tonight. How terrific is that? That's wonderful turnout.
Yeah.
My name is Mike Bush, and I do these maintenance webinars typically the first Wednesday of every month. And Charlie, you put up something that said my January webinar was the 14th. I was curious about that because that's not the first Wednesday of January. So is that correct, or is that a misprint?
I will double check on that while we're going along here. I thought we might have skipped the first Wednesday because of the fact that it was New Year's, but we can definitely go with the first Wednesday, which is the second.
Okay, well, please let me know for sure so I know what the right date is.
Absolutely.
I would hate to miss one of my own webinars. At any rate, the subject for tonight is the EGT myth. This will be a slightly shortened version of a talk that I gave on the Forums Plaza at AirVenture 2011. And we're actually going to be talking about more than just EGT. We're going to be talking about EGT, CHT, TIT, detonation, pre-ignition, bunch of stuff having to do with engine, the parameters that we measure on our engines, what they really mean, how to interpret them, and so on. And there's a lot of stuff to talk about, so let me plunge right into it, and we'll start off with a brief history of exhaust gas temperature in general aviation.
Mike, I just want to break in here for just 1 second. I did some checking, and you are correct. It's January 4th. It's all about magnetos. So we had the wrong date on the warm-up slide.
Oh, okay, fine. So January 4th.
January 4th it is.
Okay, thank you for clearing that up. At any rate, the first exhaust gas temperature gauges that we had in piston-powered general aviation aircraft started appearing in the late 60s. I remember that because my very first airplane was a 1968 Cessna 182, and it had one of these newfangled Alcor EGT gauges, which was the latest and greatest thing at the time. It was introduced by a company called Alcor, a company owned by a petroleum engineer by the name of Al Handari. And it just consisted of a little analog gauge like the one on the left side of the three on the screen, and a single thermocouple probe that was stuck into the exhaust cluster in the engine. And it read out exhaust gas temperature on that uncalibrated scale. Now, that very first EGT gauge, and the one that's pictured is actually the exact same one that was in my 1968 Skylane back then. If you'll notice, has no numbers on it. It's an uncalibrated scale. It has a bunch of tick marks on it, and each tick mark is worth 25 degrees Fahrenheit of exhaust gas temperature. And it's got some bigger tick marks, every fourth one, that represent 100 degrees Fahrenheit of EGT. But there are no numbers on the scale, so you can't look at that gauge and say, oh, my EGT is 1,575 degrees. It's simply an uncalibrated gauge. And the way that gauge was used was that one would lean the engine, and as you leaned further, the needle would keep going up until it reached a peak. If you kept leaning further, it would start back down, and you would make note of what the peak EGT was, typically by turning that little yellow reference pointer, which is controlled by a knob, to what the peak was. And you could then adjust your EGT relative to peak EGT. If you wanted to be 100 rich of peak, you could enrich it until the needle dropped 4 tick marks and so on. But there was nothing on that gauge that read out absolute values of EGT, only relative values relative to peak. And Al Al Handari was a pretty smart cookie. He left the numbers off that gauge for a very good reason that we're about to see. Later on in the 70s, we got our first what were called engine analyzers, which basically consisted of a stack of 6 of these analog gauges, all cleverly combined into a single instrument. That's the middle picture here. This is the one that Alcor had. I actually had in my second airplane, which was a Blanca Super Viking, I had a similar gauge that was made by a company called KS Avionics, Bill Simpkinson's company. But again, it was basically 6 analog meters stacked up in a single 3 1/8 inch gauge, so that you could simultaneously look at all 6 EGTs from each individual cylinder. And it was useful for all sorts of troubleshooting stuff that you couldn't do with a single probe EGT. But again, there are no calibrations on that gauge. Everything is relative. And then later on, in I believe the very late 70s, Insight Instruments came out with their very first graphic engine monitor, which is the thing that's pictured on the right side. This was the first electronic engine monitor. It had a number of very innovative features because it actually had a microprocessor inside, so it could do some pretty smart things. It used an LED bar graph display instead of a mechanical meter movement, and it displayed not only all 6 EGTs, but it also displayed all 6 cylinder head temperatures, CHTs, and it did that with that little gap in each bar. The gap represents a CHT, and the top of the bar represents EGT. You'll notice that on the right-hand side of that gem, there is a calibration scale for CHT. So you can see the CHTs are running right around 300, 325 degrees. But there is no calibration marks for EGT. Again, EGT was reported out as purely relative to peak and not an absolute value. Now the trouble began when a company called Electronics International came along with an instrument that they called the US-8 Ultimate Scanner. And this instrument, instead of showing EGTs as an analog indication or a pseudo-analog bar graph, actually put out a digital readout, so you could read absolute EGT values. For example, on this particular display, 1323 or 1365 degrees. And of course, Electronics International touted that their instrument was really accurate and would display EGT to the nearest degree Fahrenheit and so on. It was really pretty silly for reasons that we're about to get into, but somehow it worked as a marketing ploy, and pilots somehow thought that a gauge that read out an exact number must be better than a gauge that just showed an analog value without any calibration. Then a company called JP Instruments came out with the instrument that's on the right side of this slide called an EDM 700, Electronic Data Monitor 700, which quickly became, and I think still is, the best-selling engine monitor in piston GA. Electronic International came back with their version of the this EDM 700 called a UBG16 Ultimate Bar Graph. But these instruments displayed not only the bar graph, the pseudo-analog EGT indication, but actually put digital readouts down below them. So they basically tried to combine the best features, or at least the most marketable features, of the original Insight GEMS bar graph and the EI's Ultimate Scanner digital readout thing. Now, the minute these instruments started coming out with the ability to display absolute EGTs, it created all sorts of problems and all sorts of misunderstandings. And the reason is that the absolute value of EGT is a meaningless number. And the reason is, as I'm about to explain to you, that EGT, as indicated on a cockpit gauge, is not a real temperature. It's not the temperature of the exhaust gas in any meaningful sense. It's called EGT, but the number is actually not a real gas temperature for reasons we're about to get into. But the fact that these gauges were starting to read out absolute values caused all sorts of confusion. First of all, owners started being concerned when they saw these numbers getting large, because pilots are typically programmed that high temperatures are bad and low temperatures are good. And in fact, with EGT, that's not a true statement. But owners would start getting concerned that the EGT on their number 5 cylinder was higher than the one on their number 2 cylinder. They would be concerned that the EGT that they were seeing was higher than the EGT that their friends who flew another airplane of the same make and model was seeing. Some flight instructors started advising pilots to lean to a particular EGT value, which, once you understand what the EGT readout means, is a totally insane thing to do. But at any rate, the fact that these newfangled instruments were actually providing an absolute EGT readout caused all sorts of confusion, all sorts of terrible advice, all sorts of concerns on the parts of aircraft owners, and a whole lot of old wives' tales. At any rate, let me try to put this at rest by asking you to forget everything you think you know about EGT and start from scratch. And let me explain to you why the EGT value that your gauge reads out is not a real temperature, and why that absolute value of EGT is basically a meaningless number. And to do that, let me ask you to follow me through a complete combustion cycle in a cylinder in your 4-cycle aircraft engine. The top wiggly line on this graph, the blue line, represents the position of the piston. It will start at top dead center during the intake stroke, and will come down from top dead center to bottom dead center, during which it's drawing in air and fuel. Then it goes back from bottom dead center up to top dead center in the compression stroke, and it's compressing the fuel-air mixture. A little bit before it gets to the top of the stroke, the spark plug starts igniting the mixture, and it starts expanding and getting real hot. And it drives the piston down from top dead center to bottom dead center in the power stroke. Then finally, the piston returns from bottom dead center back up to top dead center in the exhaust stroke and expels the unburned byproducts of combustion and gets ready to draw in a new charge, a new fuel air charge, and start the process over again. So that's what the piston is doing during one complete cycle, 720 degrees of crankshaft rotation. Now let's move to the middle red line, which represents the temperature you would see if you were able to put a temperature probe right inside the combustion chamber. And in fact, we sometimes do that on a test stand. My friend George Brawley at Tornado Alley down in Ada, Oklahoma, does this on a regular basis. He has some tricked out spark plugs that actually have temperature sensors in them, and they can actually watch the instantaneous temperature and pressure inside the combustion chamber as this combustion event takes place. And the combustion event actually is a fairly slow thing. It takes about 6 milliseconds or so at normal cruise RPMs. So it's not anything like an instantaneous event. It's actually a fairly slow event, certainly by computer standards and so on. So let's take a look at what happens inside the combustion chamber and that's the middle line on this graph. As the intake stroke starts and the piston starts down, the exhaust valve closes. It was open for the previous exhaust stroke. The exhaust valve closes, the intake valve is wide open, and the cylinder is drawing in nice cool air with some fuel added to it. And of course, the temperature in the combustion chamber is quite low, and it gets lower and lower as more and more of this nice cool air gets drawn in. Now the piston starts back up on the compression stroke. The intake valve closes, so now both valves are closed, and we're starting to compress this mixture. As we compress it, it starts getting warmer, and then about 20 to 24 degrees of crankshaft rotation before the piston reaches top dead center, the spark plug fires. And now this fuel air mixture starts to burn, and the temperature starts to rise very, very rapidly. And it continues to rise as the piston reaches the top of the compression stroke, and even continues to rise a little bit as it starts back down, normally reaching a peak about roughly 16 degrees after top dead center, and a very high temperature, a temperature that is typically somewhere in the very high 3,000 degree Fahrenheit range, pretty close to 4,000 degrees, a very hot temperature indeed. It doesn't stay that hot for very long, and it's a lucky thing, otherwise the aluminum piston and the aluminum cylinder head would start to melt, but it only gets that hot, and it only stays that hot for a very brief instant. And then it starts cooling down as the piston moves down towards bottom dead center and extracts the heat energy from the fuel air mixture and converts it into mechanical energy, rotating the crankshaft. A little bit before the piston gets to the bottom of its power stroke, the exhaust valve starts to open, and by the time the piston is all the way at bottom dead center, the exhaust valve is fully open, and then the piston starts to go back up and push the byproducts of combustion, after all of the energy that the engine can extract from it has been extracted, push it out the exhaust port through the open exhaust valve. And of course, as that happens, the gases continue to cool. And finally, just before the piston gets to top dead center, the intake valve starts to open in preparation for the next intake stroke, and of course the process repeats. So what we're seeing on that graph is what you would see if you could put a temperature probe right inside the combustion chamber. But we don't put a temperature probe inside the combustion chamber in our aircraft. To do that involves some very exotic technology and very expensive technology. That's not what we have. What we have is an exhaust gas temperature probe, which is a thermocouple probe that is mounted in the exhaust riser, typically something like 2 inches from the exhaust port. So let's go down to curve C, the bottom curve, and consider what that exhaust gas temperature probe, the thing that is providing information to our panel-mounted gauge, what that probe actually sees. And the key thing to understand is that for roughly 2/3 of the cycle, that probe sees nothing at all interesting, because the exhaust valve is closed. Now, all sorts of interesting stuff is happening inside the combustion chamber, including a temperature rise up to about 4,000 degrees, but the exhaust gas temperature probe can't see any of that because the exhaust valve is closed, and it's on the non-interesting side of the exhaust valve, if you will. Then finally, at the very, very end of the power stroke, just before the piston starts coming up for the exhaust stroke, the exhaust valve starts to open. What happens when the exhaust valve starts to open is that some gas starts rushing out. and rushing past this exhaust gas temperature probe. And the gas that starts rushing out is very hot. But as it continues to go out the exhaust port, as the piston rises up towards top dead center, it rapidly gets cooler and cooler because the pressure has been relieved by the exhaust valve opening. So what does the exhaust gas temperature probe see? It sees a brief pulse of exhaust gas whose temperature is constantly changing. Starts out very hot, very quickly starts cooling down, and then and it sees it for about a little less than a third of the cycle, and for the remaining 2/3 or a little bit more of the cycle, the exhaust valve is closed, so there's basically nothing flowing past the probe. So now, what exactly is the temperature that this EGT probe is reporting back to the gauge? Well, it's not the temperature of the exhaust gas. It's the temperature of the EGT probe itself. And what is that temperature? Well, the EGT probe, which has a fairly significant amount of thermal mass, is looking at all of these pulses of very hot gas, punctuated by long periods of nothing at all, and trying to somehow integrate all of that rapidly moving stuff into a probe temperature, which is actually a pretty arbitrary number. It's really not the exhaust gas temperature. Well, I guess it's the exhaust gas temperature at 2 instants of time. It's kind of like a stopped clock being right twice a day. But in no sense is the EGT value that probe reports back any kind of a meaningful gas temperature. It simply, first of all, is blinded during the most interesting parts of the combustion cycle, and second, the temperature of the gas is varying so rapidly that the probe can't possibly keep up. And the best it can do is sort of settle down at some equilibrium value, which is what it reports back to the gauge. That's why I'm saying that the absolute value of EGT is basically a meaningless number. And it's affected by a lot of things other than what was going on in the combustion chamber. It's affected by probe position, it's affected by valve timing, it's affected by all sorts of things. And it's just not a very meaningful number. Okay, let's talk about what EGT really means. In fact, let's talk about what all of the gauges that we have in the cockpit that bear on engine performance are really trying to tell us. And I think the best way to get at that is to consider what happens to the energy in the fuel as it passes through our engine. It's an unfortunate fact, and particularly unfortunate in these days of $6 and $7 avgas prices, that our piston aircraft engines are rather inefficient at converting the energy latent in the fuel into useful energy that turns the propeller. In fact, under the best of circumstances, our engines only have an efficiency of about 1/3. In other words, only about 1/3 of the potential energy in the fuel actually turns out to be power to the propeller. And the other 2/3 are wasted. And all of our engine gauges are reading out waste energy. Let me go through that for you. The largest amount of this wasted energy goes out the exhaust pipe. About 50% of the energy in our fuel winds up not being extracted by the engine and simply going out the exhaust pipe at the end of the cycle, because the technology of the engine is such that it simply can't extract any more energy from the fuel than that, and so all the energy that it can extract winds up going out the exhaust pipe, and we see that wasted energy as exhaust gas temperature. If you have a turbocharged engine, We attempt to recapture a small amount of that wasted energy by putting it through a turbocharger and spinning a compressor and generating some boosted manifold pressure. But basically half of that $6 or $7 avgas winds up going out the exhaust as just simply wasted heat that the engine was unable to extract. And that is what we see on the EGT gauge. It's how much heat we're wasting out the exhaust. Another significant portion of wasted energy, roughly 1/6 of the total, is dissipated by the cylinder fins. And we measure that waste by putting a temperature probe on the cylinder head itself and measuring its temperature. Think about it. If we had a perfectly efficient engine that was able to extract all the energy from the fuel and convert it into useful work, turning the prop, then the cylinder head temperature would be outside ambient. It would be cool to the touch, because the engine was so efficient. It was extracting all of the energy from the fuel and not heating up the cylinder. But in fact, of course, our engines are very inefficient, and they heat up the cylinders quite a lot, cylinder heads quite a lot, and we measure that on a gauge called a cylinder head temperature gauge. They heat up the cylinder in several ways. Part of the heat of combustion is transferred by conduction to the cylinder. There are frictional losses involved in the piston rings running up and down inside of the cylinder barrel and generating frictional heat, which also is transferred to the cylinder head and dissipated by the fins and so on. All of that waste is what we see on the CHT gauge, and it represents around 15% of the latent energy in the fuel. A third way that we waste heat is by heating up the oil. If you think about it, the cylinder head and barrel are air-cooled because they have fins on them. But part of the combustion chamber is something called a piston. And the piston doesn't have any air flowing over it and doesn't have any fins or anything. The only way the piston dissipates its heat is by getting a lot of oil splashed on it and transferring its heat to the oil. The piston is an oil-cooled device. Even though we think of our engines as being air-cooled, the piston is not air-cooled, it's oil-cooled. And that coolant therefore heats up as it's passing through the engine, and we cool it back down, passing it through an oil cooler. And we measure the amount of heat energy wasted by heating up the oil by an oil temperature gauge. That represents a fairly small amount of waste, only about 2%. But it's important enough that we have a gauge to measure it. So we've got these three gauges in the cockpit measuring wasted energy. EGT, energy wasted out the exhaust. CHT, energy wasted by heating up the cylinder. And oil temperature wasted by heating up the oil. All things that we really wish didn't happen. We really wish we had a 100% efficient engine that converted all the energy into mechanical rotation and didn't heat up anything. But we have far from an efficient engine. We have only about a 1/3 efficient engine. We actually do have a gauge on the cockpit that measures the unwasted energy, the power to the propeller. It's called an airspeed indicator. So if you look at those four gauges, they pretty much instrument every place that the energy in the fuel goes. Now let's consider a little bit more about exactly how this energy is being wasted. CHT measures the heat energy that is wasted during the power stroke. Of the four strokes in our four-stroke engine, the only stroke that actually heats up the cylinder head and creates the heat that we see in the form of CHT occurs during the power stroke, when all the real exciting stuff's going on. and when the cylinder and piston and connecting rod and everything are under the maximum stress, because that's when the very highest internal pressures and temperatures occur. On the other hand, EGT measures heat energy that's wasted during the exhaust stroke. When the exhaust valve is open and the combustion gas is basically depressurized and is simply being shoved out of the combustion chamber by the rising piston in order to clean out the old stuff and get ready to start anew with a nice fresh load of air and fuel. So the wasted energy that occurs during the time that EGT is being produced is occurring at a time when the cylinder assembly is under very little stress. All of the high stress stuff already happened, and now by when the exhaust valve is open and the EGT probe is actually getting to see something, the power assembly, the cylinder and piston and so on, are in a de-stressed condition. So if we are concerned about limiting the stress levels that we put on our engine, if we are trying to protect it from abuse, if we're trying to make the power assemblies last for a nice long time without having to have a lot of expensive maintenance done, the number we really need to be focusing on is cylinder head temperature, not exhaust gas temperature. High exhaust gas temperature does not signify that the engine is under stress. All it signifies is that a lot of very expensive energy is getting thrown out the exhaust without doing useful work. It's a measure of inefficiency. It's not a measurement of stress. On the other hand, CHT is the closest thing in the cockpit we have that measures the stress that is being put on the engine components. And we'll see that in a couple other slides. But basically, it's very important to understand what CHT is telling us and what EGT is telling us. And the measure of stress that we're putting on an engine is reflected in cylinder head temperature. It is not reflected in exhaust gas temperature. So, limiting CHT to a reasonable value, and we'll talk about what that should be, or what I recommend that should be, is absolutely essential to limit the stress on the engine components and to ensure cylinder longevity. Limiting exhaust gas temperature is a foolish thing to do. It accomplishes nothing useful. It is not a measure of stress. You are not being kind to your engine by running it at low EGTs. There are a lot of misconceptions about that. And a lot of pilots see these very scary EGT numbers that are up around, in the 1500s or even sometimes in the 1600s in turbocharged engines, and they get all worried that they're doing something bad to the engine. That's just not the case. EGT is not a measurement of stress. CHT is what we should be focusing on. Because EGT, A, is not a measurement of stress, and B, is not a real temperature, leaning to a particular absolute EGT value, as I've seen a number of CFIs teach their students, makes absolutely no sense at all. The absolute EGT value is a meaningless number, and leaning to some particular number like 1400 or something is simply nonsensical. It's just really bad advice from people who don't understand what EGT means. Now, in a turbocharged aircraft, we typically have another readout called turbine inlet temperature, or TIT. And TIT is measured with exactly the same kind of thermocouple probe as EGT. The only difference between a TIT gauge and EGT gauge is where the probe is located. In the case of a TIT probe, which we only have on a turbocharged aircraft, the probe is located as far downstream in the exhaust system as possible, preferably right near the inlet to the turbocharger's turbine section. If you have a temperature probe located way downstream like that, where it's measuring not the output of just one cylinder, but it's measuring the output of all 4 or 6 cylinders combined. And if it's way downstream, so that all of the pulsiness has had a chance to equalize, and so that it's actually measuring basically a continuous gas flow at more or less a constant temperature, now its reading becomes meaningful. Now its reading is actually, the absolute value is actually a meaningful number. And we typically do, in turbocharged aircraft, measure the TIT and try to limit it to some redline value, typically either 1650 or 1750 degrees Fahrenheit, in order to protect the turbocharger's turbine wheel from overtemping. But that's a whole different situation than what EGT measures. EGT, the probe is mounted near the cylinders, close to the exhaust port. Typically, with an engine analyzer, it's measuring only one cylinder's output. It's seeing a very, very pulsy value, and the temperature it reports is not a real gas temperature. It's just sort of some equilibrium level that the probe winds up at after seeing all of this highly changing gas temperature. Another thing that I'd like to disabuse you of is one of the myths that has been going around ever since these engine analyzers have been available, and that is that somehow a healthy engine should have all of its EGTs the same. It's what I call the flat top myth, which is that we really want to see all those bars at the same level. And for all the reasons that I just explained to you, that makes no sense. Variations in EGT from one cylinder to another are perfectly normal. They can frequently be affected by probe placement, by exhaust plumbing geometry, and so on. For example, in my airplane, I fly a 79 Cessna T310R. The number 5 and number 6 EGTs, those are the two front cylinders, are always lower than the other ones. The reason that they're always lower is because the exhaust risers to those front cylinders curve backwards, whereas the exhaust risers to the 1, 2, 3, and 4 cylinders go straight down. And so the exhaust flow through those exhaust tubing are different, and the probes that are placed into those exhaust risers see different flow patterns and report back different temperatures. There's nothing wrong with the engine. The engines are as finely tuned as they possibly can be. I can run them at 100 lean a peak before they start getting rough. They're perfectly tuned engines. My EGT display is definitely not flat top. The 5 and 6 temperatures are lower than the others for a perfectly plausible reason that has absolutely nothing to do with anything being imbalanced in the engine. So we're not looking for equal EGTs. What we're actually looking for is minimum what's called a GAMI spread. This is a diagram, and it's a 4-cylinder engine, just so that the graph isn't quite so busy, but it would be exactly the same if it was a 6-cylinder engine. This is a graph that is plotting the reported exhaust gas temperature for each of 4 cylinders plotted against fuel flow, and where the right of the graph is very, very rich and the left of the graph is very, very lean. And you can see as we lean the engine from full rich, the 16-gallon-an-hour side, and move it leaner and leaner, the various EGTs rise, and then they reach a peak at some point and start back down. And because the mixture distribution in any engine is not ever going to be perfect, the peaks don't all happen at the same point. In this particular engine, the number 1 cylinder, the red curve, reaches peak first as we lean, because that cylinder is running at a somewhat leaner mixture than the others. And then the green one peaks next, and then the blue one peaks next, and then the purple one peaks last. And that's typical of any engine. Now, if you look at the differences in absolute EGT, which would correspond to, let's say, the raggedness of the multi-bar EGT display on an engine monitor, you'll see that that you will get the flattest top. In other words, the minimum difference between EGTs at a mixture that's very close to peak EGT, which is probably not where we want to run this engine if we want it to last very long. And you'll see that the maximum difference in EGTs occur when we're either fairly rich or when we're lean at peak, which are the two places we probably do want to run this engine if we want to get a reasonable life out of it. So, you know, if you're trying to lean this engine in order to get a nice flat top, you're probably not doing it any favors whatsoever. The number that we're really interested in is what's called the GAMI spread, and that is the difference in fuel flow from where the leanest cylinder peaks, that is, in this case, the red one, compared with the fuel flow where the richest cylinder peaks, in this case, the purple one. In this particular engine, 1 is the leanest cylinder and 3 is the richest cylinder. And if we make note of the fuel flow where each of the cylinders peaks, we'll see that in this case we have an engine with a GAMI spread that looks to be roughly 0.4 of a gallon an hour. And that's a very good number. If you have a GAMI spread of 0.4 of a gallon an hour, you're doing pretty much as well as you're going to be able to do in tuning that engine. Most engines come out of the factory with GAMI spreads that are much larger. Typically for injected engines, they're typically up around 1 gallon an hour. For carbureted engines, they can be 1.5 gallons an hour. And by carefully tuning the injectors and so on, we can narrow that GAMI spread, and we really try to tweak the nozzles and so on to get that spread to be 0.5 gallon an hour or less, and that makes for a very, very smooth running engine that will run smoothly at very lean mixtures and so on. But it's the GAMI spread that we're interested in minimizing, not the difference between the different EGTs. Trying to do that is misguided. Here, for example, is a TCM IO550B engine. That's a Bonanza engine. Right as it came out of the crate with standard TCM fuel nozzles. And if we take a look, we can see, excuse me, that if we look at where the richest cylinder peaks and the leanest cylinder peaks, the difference is about 1.3 gallons per hour. And that's typical of an engine with stock non-tuned injectors, and it's much higher than what we would like it to be. And we took this engine and we tuned the nozzles, put in a set of tuned nozzles, and then repeated the test. And now the GAMI spread, it was down to 0.4 gallons an hour, which is very, very good. Again, you can see that even with this very finely tuned engine, the peak exhaust gas temperatures for the different cylinders are very different. We don't get anything close to a flat top on our gauge. But what we do get is a very nice low GAMI spread, which is what we're interested in. So, what good is exhaust gas temperature? Why are we interested in having that? I'm pausing for a minute because my little thing is saying that my new slide hasn't come up.
Mike, I'm seeing the EGT. So what good is EGT slide?
Okay, you are seeing. For some reason,
Yes.
I've got a red bar, but I'll ignore it. Anyway, what good is EGT? It is fantastic for troubleshooting. The right way to use these numbers is to use CHT as your primary guide for power plant management. In other words, where you set your power settings, where you set your mixture in order to get maximum longevity. And use EGT to ensure that everything's working properly and to help diagnose problems when they occur, detect and diagnose problems where they occur. And so let's just quickly talk about some anomalies that we might see in EGTs and what they mean. A magneto that's malfunctioning will cause EGT to rise on all the cylinders. The CHT will remain normal or actually maybe slightly depressed because the cylinders produce a little bit less power with one spark plug firing than they do with two. But the EGTs will all rise, typically somewhere between 50 and 100 degrees. One mag going out will typically, the engine will continue to run smoothly, but you'll have all of the EGTs simultaneously rise to above normal levels. And if you have alarms set in your engine monitor, the alarm very likely will go off. If this happens, we suspect a malfunctioning magneto, and if it were me, I would confirm the diagnosis by doing a quick in-flight mag check. But in fact, if one of the magnetos is not working, has stopped working, then when you switch the engine to that magneto, it will quit. So you might not want to do this if your wife's in the airplane, but if I was in the airplane alone, I would definitely do a quick mag check and confirm that, yes, I have a dead mag. A defective or fouled spark plug, or more rarely an ignition lead that goes bad, will cause elevated EGT, but only on the one affected cylinder. So if we have one cylinder whose EGT suddenly rises, in this particular case, it looks like it's the number 5 cylinder that did it. The number 5 cylinder on the left engine. This is a twin engine display. This is basically the gauge I have in my airplane. Then we know that one of the spark plugs in cylinder number 5 has stopped firing. This is not a magneto problem, because magneto problems will affect all cylinders simultaneously. This has to be a spark plug problem, or more rarely an ignition lead problem, but most likely a spark plug problem. Again, we should confirm this by doing an in-flight mag check, and when we switch to the mag that is firing, that is connected to the non-firing spark plug, that number 5 EGT that's higher than normal will suddenly go cold, and the engine will start to shake a little bit because it's running on 5 cylinders instead of 6. And then we go back to both and everything is normal, and we make a note of which mag we were switched to when the number 5 cylinder went cold, and we will know from that information exactly which spark plug, whether it's the top or the bottom spark plug, is the culprit. And then when we get on the ground, we can go change that spark plug or clean it out or whatever we have to do. A partially clogged fuel injector nozzle in an injected engine will cause different symptoms depending on whether you're rich of peak or lean of peak at the time that it happens. If you're lean on the rich side of peak, a partially clogged fuel injector nozzle will cause both EGT and CHT to rise on the one cylinder that has the partially clogged nozzle. If, on the other hand, you're lean of peak, both EGT and CHT will fall on the cylinder that has the partially clogged nozzle, and most likely the engine will start running a little rough, because if you're lean of peak and you get a partially clogged nozzle, that cylinder may actually get to the point where it's not producing power anymore. If you suspect that you have a partially clogged nozzle based on these indications, go full rich. I would actually turn on the boost pump momentarily. Sometimes, if you increase the fuel flow by going full rich and turning on the boost pump, you can wash the clog out of the nozzle and everything will come back to normal. If you can't do that, then land and dump your engine monitor data, and it will be pretty obvious what's wrong, and you'll know which nozzle to have cleaned and so on. If a fuel injector nozzle is completely clogged, then that will just shut down the cylinder, because obviously it's not going to be able to run with no fuel coming in. And the engine will get real rough, and the one cylinder that has the clogged nozzle will go cold. The EGT will go cold. Again, if this happens, you can attempt to unclog by going to a full rich mixture and momentarily going to high boost on your boost pump if you have, assuming you have all that stuff. Almost every aircraft with an injected engine has to have a boost pump as well by regulation. And if you can't clean out the nozzle that way, then you're simply going to have to reduce power, accept the roughness, and land as soon as practical, because you're flying a 5-cylinder engine instead of 6-cylinder, or even worse, a 3-cylinder engine versus a 4. 5-cylinder engines run moderately rough on, 6-cylinder engines run moderately rough on 5. 4-cylinder engines run really, really rough on 3. So if it's a 4-cylinder engine and you lose a cylinder, you're probably going to want to land like really, really soon. So once again, to review, limiting cylinder head temperature is the key to engine longevity. We really want to operate these engines as temperature-limited engines, just like we would a turbine. But the limiting temperature, the one we want to focus on, is cylinder head temperature. It's the best proxy we have for the peak cylinder temperatures and pressure, and the amount of stress that we're putting on our critical engine components. So we want to keep those under control. Limiting EGT is not helpful. It's not a measure of engine stress. In fact, lots of things that cause EGT to rise, like say a failed magneto, actually reduce stress on the engine. The engine's producing less power, but EGT has gone up because the magneto has failed. EGT is primarily useful for troubleshooting. CHT is primarily useful as to keep the engine within operating limits that will assure maximum engine longevity. Here's a graph that shows the tensile strength of our aluminum alloy cylinder heads as the cylinder head temperature rises. And this slide didn't quite come out the way I expected it to, but at 400 degrees Fahrenheit cylinder head temperature, the head has lost half of its tensile strength, and it continues to lose strength very rapidly as CHT rises above 400. TCM engines typically have a CHT redline of 460 degrees. Lycomings are even worse. They typically have a redline of 500 degrees. Those temperatures are emergency temperatures only. We never want to get anywhere close to those temperatures for reasons that we're about to see. My personal EGT or CHT redline is 400 degrees Fahrenheit, and my maximum target is 380. I try never to let any one of my cylinders operate above 380. If I see cylinder head temperature rise above 380, I start to do something to bring it down. If I ever see it get to 400, I do something right now aggressive to bring it down. To me, 400 Fahrenheit is my personal red line. I guess this slide is the one that's showing that. So that color bar graph on the bottom represents sort of my mental cylinder head gauge markings. That's definitely not where the manufacturers set the red lines. They set them way up higher than that, but that's where I set my own personal red line for maximum engine longevity. And obsessive attention to these temperatures, I think, is one of the reasons that my engines are now at 200% of TBO and doing pretty good. CHT, as indicated, is the best proxy we have for stress on the engine's key components. If you plot cylinder head temperature and you plot peak pressure, you'll see the curves are the same shape and they peak at about the same point. CHT is something we have instrumented in the cockpit. Peak pressure, it would be very nice to have instrument in the cockpit, but at least so far, we can only instrument that on a test stand. So the CHT is the closest proxy we have in the cockpit for peak pressure, and peak pressure is what really counts in terms of engine stress and engine longevity. Both of these curves reach a peak at a mixture of about 40 degrees rich of peak. So 40 degrees rich of peak is the worst possible place to run these engines. Amazingly enough, lots and lots of POHs recommend operating engines at 50 rich of peak, which is very close to this worst area. That's because these POHs were written typically back in the 60s when nobody knew any of this stuff. We're a whole lot smarter now. But that's the worst possible place you can run an engine. We don't want to let our cylinder head temperatures and our peak pressures get that high. We want to stay out of those peak areas. How do you do that? Well, there's two ways to do that. One is to avoid the mixtures that get us into that area. So you can see that to avoid being in that area, we either need to run the engines quite rich or a little lean of peak. Either one will get us out of that area. The slope of these curves is very shallow on the rich side of peak, and it's quite steep on the lean side of peak. So it takes a lot of richening to bring the CHT down and the peak pressure down. It takes a little bit of leaning on the lean side to do the same thing because the curves are much steeper. The other way we can stay out of the bad areas is to reduce power. If you pull the power back to 55 or 60%, then you can pretty much put the mixture anywhere you want and not be in any of the critical areas. So the two ways that we can avoid overstressing our engine components is either to lean correctly in order to keep cylinder head temperatures at a reasonable level, or reduce power to do the same thing. Your choice. Here's a page out of the TCM operating manual for the IO550B engine. It shows EGT and CHT and horsepower and brake-specific fuel consumption curves and how they vary as we change the mixture with richer on the right, leaner on the left. Again, you'll see that there's peak EGT. You'll see that peak cylinder head temperature, which is also peak stress on the engine, occurs about 40 degrees rich of peak. This particular graph, when we are lean to 40 degrees rich of peak, the engine is putting out 83% power. And the cylinder head temperature is up about 425 degrees, which is way too hot. And if you run it there, you're going to be doing top overhauls on a fairly frequent basis. If we want to bring the cylinder head temperature down to 400 degrees from 425, we have a choice. We can either go way rich, in this case 160 degrees rich of peak, or we can lean to 10 degrees lean of peak. Either one will have the same effect of bringing the cylinder head temperature down to 400 degrees, and both will have the effect of bringing the power down from 83% power to 80% power. So we've lost about 2% of power. Airspeed varies with the square root of power. So if we lose 2% of power, we lose, what, 1.4% of airspeed? Hardly enough to notice. So if we can make our engines live long and prosper by reducing by leaning to reduce power by 2% and airspeed by 1.4%, that's a pretty darn good trade-off. If we want to go further and bring the cylinder head temperature down to 380, which is where I like to see mine go, we either have to lean to 35, lean a peak, or we have to rich into something way off the chart. Basically full rich in this case, I think. And if we did either of those things, the power would go down further from 80% down to 77%, and we would lose airspeed of maybe 2–2.5%. Still a pretty reasonable trade-off in my view, but that's pretty much how the numbers go. And whatever engine you're flying behind, you can go to Continental or Lycoming and get an operator's handbook that'll have graphs like this, and you can kind of see how this all works for your own engine. But since all of these engines use basically the same componentry and the same physics, and physics is the rules of physics are pretty much the same everywhere, the curves for your particular engine are likely to look very, very much like these curves for the IO550 Continental. Now, cylinder head temperature is not a perfect proxy for internal for peak pressure and peak stress. It's affected profoundly by that, but also by a couple other things like outside air temperature, whether we're at a slow airspeed climbing or at a faster airspeed cruising or descending. It's affected by air density, so up at real high altitudes where the air is very much less dense and there are not a lot of air molecules passing through past the cylinders, we will have a loss of cooling efficiency and increased CHT. It's also affected by the design of the aircraft's cooling system. Modern designs like the Cirrus and Diamonds, for example, have much more efficient cooling systems than older designs like the Cessna 310 that I fly, that was originally designed back in the 50s when engineers really didn't know very much about this stuff. So we can't use CHT exactly as a measure of stress. We have to adjust it a little bit. For example, if you're flying in very cold temperatures, you probably want to lower your target CHT a little bit. If you're flying at very high altitudes, you probably need to raise it a little bit. But CHT, again, is the best proxy we have in the cockpit for measuring stress on the engine, so it should be the primary gauge that we look at when we're deciding how to manage the power plant. Engine cooling system, just very quickly, most aircraft engines are cooled like this, or a couple that are sort of upside down from this, but this is the most common arrangement. We create a high pressure area above the engine and a low pressure area below the engine, and we do that by setting up a series of baffles and baffle seals and inner cylinder baffles that basically partition the engine compartment into two airtight chambers, a high pressure area above, a low pressure area below. The high pressure is created by blast or by ram air coming into the cowling inlets, and the low pressure is created by a gap in the lower cowling that may either have cowl flaps on it or may just be a fixed orifice that creates a vacuum down there. So if we have high pressure above the engine and low pressure below the engine, and the baffles are all correct, then the only way the airflow, the pressures can equalize and the airflow can pass from high pressure to low pressure is by going through the cylinder fins. If any of those baffles are missing or incorrectly placed, then air can pass from high to low without going through the cylinder fins, and we have a big loss in cooling efficiency. Do you know your CHTs? Obviously, I've tried to make the point that CHT is the most important parameter for managing the power plant. But you don't know your CHTs unless you have a probe per cylinder analyzer. If you're still flying an airplane that only has a single probe factory gauge, or worse, an airplane with no CHT gauge at all, you don't know what your CHTs are. If you have a factory single probe CHT gauge, you know CHT on one cylinder, but you don't know anything about the other cylinders. And that one cylinder that you're looking at could be nice and comfortable, but one of the others that you're not looking at could be getting itself cooked to death. This actually kind of strikes home particularly today, because this afternoon I was contacted by an aircraft owner down in Mexico who had a head-to-barrel separation in his Cessna 210, scared the living daylights out of him. This particular separation occurred on his number 3 cylinder. The number 3 cylinder had consistently been running hotter than the others. He had an engine analyzer. His mechanic basically said, don't worry about it. They all do that, which, by the way, is a big red flag. Anytime a mechanic says, don't worry about it, they all do that, go get a second opinion. But at any rate, he's been flying along with this hot cylinder number 3, not worrying about it, and it came apart on him. The cylinder head temperature was high enough that it compromised the tensile strength of the cylinder head casting, and the casting failed at the head to barrel junction, and kind of made him fall out of the sky. He was able to get it back down on an airport where he is now stuck, because it's an airport that doesn't have any services, and I'm working with him to try to get him rescued. It's down in Mexico someplace. But this engine was talking to him for a long time, and with the dubious advice of his mechanic, he wasn't listening, and the result was that the cylinder came apart, and exactly the cylinder that had been running hot for a long time. So we need to have good instrumentation. We need to pay attention to it. How do we reduce cylinder head temperature? If you have cowl flaps, open them. If you can increase your airspeed, particularly if it's a high cylinder head temperature during the climb, flatten the climb, get more airspeed. Adjust the mixture, either richer, maybe full rich, or if you're running lean to peak, lean it some more to bring the temperature, the cylinder head temperature down. And if all else fails, reduce power. Do what it takes to keep the cylinder head temperatures under control and within reasonable parameters. Now, the last thing I'm going to do before we go to question and answer is just say a couple of things about some abnormal combustion events called detonation and pre-ignition. Those are the 2 worst things that can happen to your engine, or at least to your cylinders. And I want to talk just briefly about what they are, and what they look like on engine instrumentation, and what you do if it happens. So let's talk about detonation first. The combustion event, as I mentioned, is something that takes a significant amount of time. It is not an explosion. It is not an instantaneous event. It's actually a fairly slow process of combustion that takes roughly 6 milliseconds and roughly 90 degrees of crankshaft rotation in most of our direct drive engines that are operating at normal cruise RPMs. And it starts about between 20 and 24 degrees before top dead center when the spark plug fires, and it proceeds through top dead center. It reaches a peak pressure point around 15 to 20 degrees after top dead center, optimally around 16. And then gradually fades away as the power stroke continues and the piston proceeds down. If we put a pressure gauge inside the combustion chamber, the way they can do in a test stand, and watch the instantaneous pressure as all of this plays out, we would see the bottom little dotted line would be the pressure if we had the mag switch off and we were just motoring the engine. And of course, the pressure would rise a little bit as the piston got to top dead center and come back down, but it would never get very high. Maybe 100, 150 psi tops. But when we put fuel in there and we put a spark in there, real exciting things happen, and the pressure rises very rapidly. Starts to rise right at the point of ignition and continues to rise through top dead center, reaches a peak, as I said, optimally up around 16 degrees after top dead center, and then starts coming back down. And that's a normal combustion cycle if we were able to measure the instantaneous cylinder pressure. Peaks out around 800 psi on a normally aspirated engine. On some boosted turbocharged engines, the peak can be as much as 1,000. It's really important that that peak happen at an appropriate time. If it happens near top dead center, really bad things can happen, because when the piston is at top dead center, the geometry of the connecting rod and the crankshaft throw are such that the pressure in the cylinder can't be converted to rotational energy. And so the pressure just builds up almost without bound, and eventually will damage the piston and the cylinder head. Usually the piston first, as we're about to see. But basically, if we have a combustion event which reaches peak pressure near top dead center, we pretty much have a pipe bomb. On the other hand, if the timing and everything is correct so that the peak pressure occurs around 16 degrees past top dead center, where that pressure can effectively be turned into rotational energy of the crank, which is the way the engine's supposed to work, then we don't have a bomb, we have a gun. We're driving the piston, aka the bullet, out of the barrel, and things don't come apart. So if the combustion event proceeds too rapidly or starts too early, and so the peak is too close to top dead center, it's too early, we get excessive temperatures and pressures, when the temperature and pressures get to be enough, the fuel air mixture starts to go unstable, and we start getting pressure pulses, very high pressure pulses, that are known as detonation. Those can come in all sorts of flavors. They can be real light detonation, they can be moderate, they can be heavy to the point of being destructive. Detonation is not a binary event that you're either in detonation or not. It comes in all kinds of strengths. But heavy detonation can be quite destructive to the engine. And when we do this on a test stand with a pressure gauge in the cylinder, we can see the detonation very clearly as ringing on that normally nice smooth pressure curve, showing that things are getting unstable, and there are these pressure waves that are called detonation. Detonation is not necessarily harmful. Light detonation happens all the time. It's not optimum, but the engines can withstand it. Typically, the detonation keeps everything nice and clean by kind of bead blasting the combustion chamber. But when detonation gets heavy, it can cause all sorts of damage. It can fracture spark plug insulators. It can damage piston rings. It can produce pitting of the piston crown, and I'll show you that in a picture in just a moment. And it can cause heat distress, even corner melting of the piston. Even if it happens enough, it could cause a head-to-barrel separation. And if the detonation results in thermal runaway, it can even lead to pre-ignition, which is a much more devastatingly destructive event that we'll talk about in just a moment. If you keep cylinder head temperatures below 400 degrees Fahrenheit, destructive detonation is essentially impossible. So if you are really attentive about CHTs and make sure they never get too hot, you don't have to worry about detonation happening. Conversely, if detonation starts to happen, the way you will know is that cylinder head temperature will start to rise to abnormal levels, and you need to do something immediately to stop it in order to protect the engine, typically yanking way back on the throttle and then sorting things out. Here's an example of a piston that was damaged by detonation. First of all, if you look at the piston crown, you'll see all these little things that look like somebody beat on it with a hammer, and those are detonation signatures. And you'll also see that this particular piston, which was subject to extreme detonation, got so hot that the corners of the piston crown started to melt, and they melted to the point where the #1 compression ring was compromised, and at that point it shut down the cylinder. Pre-ignition is a different phenomenon altogether than detonation, although detonation can lead to pre-ignition. But detonation, I mean, pre-ignition is the ignition of the spontaneous ignition, if you will, of the fuel air charge that occurs prior to when the spark plug fires, because something in the combustion chamber has gotten so hot that it is acting like a glow plug and ignites the fuel air mixture prior to the time it's supposed to be ignited by the spark plug. The ignition source can be anything in the combustion chamber that is capable of glowing red hot. It can be an overheated spark plug tip. It can be a fractured spark plug insulator. It can actually be carbon or lead deposits in the combustion chamber. But anything, any foreign material, if you will, in the combustion chamber that heats up to the point where it starts glowing red has the potential for being the ignition source for a pre-ignition event. And when pre-ignition occurs, of course, the fuel air charge ignites early in the compression stroke rather than at the very end of the compression stroke when it's supposed to, so that the fuel air mixture starts expanding while the piston is going up, and it causes a tremendous amount of heat, mechanical stress, typically far beyond the design limits of the engine. And once this happens, substantial damage to the engine is almost inevitable. No engine can survive pre-ignition for more than a few seconds without something letting go. Here is an example of a pre-ignition scenario. This one was in a Cirrus SR20 with a Continental IO 360 ES engine. And basically what happened was the pilot applied full power for takeoff. What we're looking at here are strictly the CHTs. I've taken the EGTs and everything off, and we're just looking at CHTs. All the CHTs started to come up normally, as you would expect when the engine went to full power. But within a minute or two after takeoff power was applied, the number one CHT, I believe that's the number one CHT, started a thermal runaway, started rising extremely rapidly. It rose up to 500 degrees Fahrenheit, at which point the engine monitor, which in this case was an Aviation MFD, was incapable of monitoring any further, because the software in the Aviation doesn't know how to deal with CHTs above 500 degrees Fahrenheit. But we would estimate, based on seeing other events like this that are with different kinds of engine monitors, that the CHT probably reached 600 to 650 degrees Fahrenheit before destroying the piston, at which point, of course, the thermal runaway was self-correcting because the cylinder got shut down. The point I want to make here is that from the time that CHT passed 400 degrees Fahrenheit to the time the piston was destroyed was less than 2 minutes. So if you have thermal runaway of a CHT, you don't have very much time to react. Here is what the aftermath of that particular event was. So, just to quickly summarize, relative EGT is a meaningful number, absolute EGT isn't. The number we want to limit in order to protect the engine is CHT, not EGT. Never lean to an absolute EGT value, because EGT values are meaningless. We are not trying to achieve equal EGTs. We're trying to achieve a minimum gamma spread. We use EGT primarily for troubleshooting. We use CHT primarily for power plant management. And for optimum longevity, and to avoid the risk of detonation and possibly pre-ignition, always keep CHTs below 400 degrees, preferably below 380. And if you ever see cylinder head temperature rise above 400 degrees and rising rapidly, throttle back right now, because you have 1 or 2 minutes before the engine will be destroyed. That's it.
Great, Mike. Could you define GAMI for us?
Oh, GAMI are the initials of General Aviation Modifications, Inc., which is George Brawley's company down in Oklahoma that that invented and STC'd GAM ejectors, which are precision-tuned injectors designed to make injected Continental and Lycoming engines have a more balanced mixture distribution and capable of running at very, very lean mixtures without running rough.
Okay, and Andy's a student pilot. He'd like to know, will a normal run-up cycling the mags cause an afterfire, specifically a Rotax 912, which is at 4,000 RPM on standard run-up mag check?
It should not cause an afterfire, and if it does, there's something wrong, probably retarded ignition timing or something. An afterfire, by the way, occurs when, for some reason, the exhaust valve opens before the combustion event is quite finished, and unburned fuel and air wind up going out the exhaust and combusting in the exhaust plumbing as opposed to inside the cylinder. Most common reason for that would be retarded ignition timing. Could happen if there was a non-firing spark plug, so that the combustion event was slower than it should be. Could conceivably happen if you were doing the run-up at excessive RPM. Those are the things that occur to me offhand that could be responsible for afterfire.
All right, and Thomas says, my CHT runs at 425 degrees in high altitude, long climbs at high air temperatures, but comes down to 380 for cruise. Should I worry?
Yes. Absolutely.
Okay. Any more on that, or is that your final answer?
Well, you first of all, you want to make sure that you have enough fuel flow. Most common reason for excessive cylinder head temperatures in a climb is that we're not getting enough fuel. I don't know what kind of airplane this is. If it's a fuel-injected airplane, you can adjust the fuel flow. If it's a carbureted airplane, you may have to pull the carb and have the main jet opened up a little bit. Other things that need to be checked are the baffles and baffle seals to make sure that the cooling efficiency is what it is supposed to be. And if all else fails in hot weather, do what I have to do, which is climb at a higher airspeed and get more cooling air past the cylinders. But yes, you do not want to be climbing at 425 degrees. That's very abusive. Also, it puts you at risk. If something should go wrong, it gives you almost no time to react.
Okay, a couple of questions along the same line, but this one's from Art. So we know that running CHTs too hot can be destructive for an engine. Can running CHTs too cold be destructive? How cold is too cold? I have an IO550N.
Excellent question. Very good question. The answer is that, with one exception, too cold is not a problem. The one exception to this, and it usually has to be pretty darn cold before this is a concern, is if cylinder head temperatures get too cold, the lead scavenging agent in the fuel, which is a chemical called ethylene dibromide, will not be able to do its job effectively, and you'll start seeing the buildup of metallic lead in the combustion chamber. And the way you normally spot this is when you pull the spark plugs. If the spark plugs have a significant amount of little balls of lead adhered to the electrodes and the insulator, then you got a problem, because if there's lead on the spark plug, there's going to be lead in other places like the cylinder head and the piston crown and so on. Now, I normally only see that in airplanes that do a lot of low power operation, like pipeline patrol and fish spotting and that sort of things, where they're flying around for hours at 50% power. Or we used to be involved with a bunch of FBI surveillance airplanes, same deal, where they were just kind of sitting up there at very low power, you know, looking down at bad guys. And for normal operation, where you're cruising in, you know, 65–75% power, rarely is poor lead scavenging a problem. But basically, the bottom line is, if your spark plugs don't have a bunch of lead building up on them, your cylinder head temperature isn't too cold.
All right. Question from Tony. Excuse me, Tony. How about the rule of thumb from the old days with no EGTs, lean to rough, rich to smooth?
Actually, interestingly enough, if you are operating an aircraft with basically no engine instrumentation, that old rule is probably about the best you can do. And I would modify it just ever so slightly by saying, lean to the onset of perceptible roughness and richen only as far as necessary to make that perceptible roughness go away. Don't, I mean, I see a lot of people who use that rule and then give the mixture control another half turn or turn, just, you know, for good measure, and that's not a good idea. You want to, if you're running without instrumentation and you want to lean by the feel method, the place you want to run is absolutely as lean as you possibly can get without the engine starting to complain.
Okay. Janine has a question. In cruise flight on our EDM 700, we had one CHT go to 450 suddenly in our 0470K. EGTs all stayed unchanged. What does that indicate?
Let me just make sure I understand the question. One CHT suddenly went to 450 degrees?
Yes.
Okay. Well, that's easy. CHT is incapable of going suddenly to anything. So if it goes suddenly, it's probably an instrumentation problem. If it took a minute to go from 400 to 450, then I would say it's probably a real problem, and we'd need to look into it. Again, the best way to determine that, because you typically aren't sitting there staring at the gauge with a stopwatch in flight, is anytime there's any sort of anomaly like that that catches your attention, the minute you get on the ground, you want to dump the data and then bring it home and graph it. And if you don't understand what you're looking at, dump the data and email it to me, and I'll take a look at it and give you my impressions. But anytime there's any sort of an anomaly on the engine monitor, first thing you want to do when you get on the ground is dump the data so that either you or some expert can take a look at it and interpret it. It's always trivial when you're looking at the data that you've dumped out of the instrument to determine whether a problem is a real problem or an instrumentation problem. They look completely different when you look at the data.
Okay, Ron's comment or question is, I put a CHT spark plug ring and a bayonet on the same cylinder. The bayonet reads 40 degrees Fahrenheit lower. Which one should I believe?
Believe the bayonet, and that's absolutely standard. A spark plug gasket probe will almost always read right about 40 degrees hotter if it's the bottom spark plug. Sometimes it will read even hotter than that if it's the top spark plug. The standard by which cylinder head temperature is measuring it at the threaded probe boss that's on the bottom of the cylinder. And if you measure it anywhere else, you're going to get a different number. So the best place to measure it is always where the manufacturer intended you to measure it, which is in the threaded boss on the bottom of the cylinder head.
Okay. Let's see. Bill has a question. So in our Cessna 180 or C-180, I assume it's Cessna 180, with the TCM 0470, we have a 6-cylinder engine monitor. If we typically fly 6,000 to 10,000 feet MSL full power and CHTs all stay in 350 to 375, if we enrich it just rich of engine roughness, all is good, right?
Absolutely. All is good.
Okay, so
Keep
that's
on
like
doing
the
what you're doing.
ideal situation.
Keep on doing what you're doing.
Okay.
By the way, the
Yeah.
0470 is probably about the most bulletproof engine that Continental ever built. And if you keep the temperatures good, it will. It's an excellent candidate for going way, way beyond TBO.
Okay.
Which is the subject of a whole other webinar, of course.
Right. A couple of questions. Let's see here about shock cooling. What is shock cooling? And then shock cooling, is it a myth?
What is shock cooling? Well, shock cooling is the inappropriately rapid cool down of a cylinder. Is it a myth? 98% yes. I used to worry about shock cooling in the bad old days before we had proper instrumentation. I used to be one of these obsessive guys, because I am obsessive about almost everything in terms of my airplane, that used to religiously start cooling the engine 10 minutes out and reducing 2 inches of manifold pressure every 2 minutes and all that kind of nonsense. And then finally I installed a really good digital engine monitor that measures cylinder head cool down rate of change and alarms when it gets too high. And I discovered that it's damn near impossible to shock cool those things. I have had a few times, very few, where the cool down alarm went off. The last time I remember, which was probably 5 or 6 years ago, was when I was at 17,000 feet and Bradley approach control basically cleared me for an ILS approach so close into the marker that I basically had to make a vertical power off dive to get there, and the cool down alarm went off, and I absolutely knew that I was abusing the engine, but it was pretty clear that night that if I said unable, they were going to put me back at the end of the line, and I'd probably run out of gas before I landed. So I just made the choice to do a bad thing to the engine. But it's very, very hard. You have to really work hard at it to get the cool down rapid enough to be a problem. And that's something, as I said, that I didn't know until I had proper instrumentation on my engine and could actually see what the cool down rates are. But if you, as long as you don't go through these, massive throttle changes from full throttle back to idle, you're not going to have to worry about shock cooling the engine.
Okay, and Reed has a follow-up question. Engine monitors have adjustable cool down alarms. What are reasonable values for the alarms?
Let me think for a minute.
Is there a reference, any reference material on that?
I have this vague memory, and that's always dangerous, that Lycoming actually has some guidance on that. I don't believe Continental has any guidance on it. And I believe that Lycoming's guidance, and boy, this is just reaching way back into some neurons I haven't used for a while. I think Lycoming's guidance is that they want you to avoid cooling down the cylinders, the CHTs, faster than 60 degrees Fahrenheit per minute. And if I'm not mistaken, in an abundance of caution, I have my own CHT or cool down alarm set at 30. And as I said, it rarely goes off at 30.
Okay, and John has a question. Have you any experience with leaning a carbureted engine with a power flow exhaust? Mine doesn't run rough when leaning with the power flow like it did before with a standard exhaust.
I actually don't. I've got 4,000 hours in Cessna 182s and stuff, but I've actually never flown an airplane with a power flow exhaust. I would guess that because the power flow exhaust is a tuned exhaust, that helps equalize some of the airflow problems, airflow and exhaust flow problems that happen with standard exhaust, that it probably should help some. And so I'm not surprised that you're saying that you can run leaner without roughness with the power flow. But I don't have any personal experience flying with that exhaust system, so I can't answer from personal experience.
Okay, and Jim says, so if I only have an EGT gauge, is it essentially worthless without knowing CHT?
Yeah, like I said, if you had to choose between only having EGT instrumentation, only having CHT instrumentation, I would take CHT every time. But it's also really important to instrument each cylinder individually, because if you're only instrumenting the CHT on one cylinder, you just don't have any idea what the others are doing. And as you saw from that destructive pre-ignition event I showed you, where cylinder number 1 just went through the roof and melted the piston, if you had factory instrumentation that was only looking at 5, for example, you'd never see that. You'd get no warning of that. All of a sudden the engine would crater. So it's really, really important to have good instrumentation. And another quick comment, I hear a lot of aircraft owners who think who seem to be of the opinion that electronic engine monitoring, modern instrumentation, is only really important if you've got some really high performance exotic airplane with turbocharging and all that stuff. My view on that's just totally the opposite. I fly a piston twin with 2 6-cylinder turbocharged engines. If I have a head to barrel separation on one of my cylinders, I shut down the engine, feather the prop, and continue to fly the airplane thinking, boy, this is going to be really expensive to fix. If I have a head-to-barrel separation on a Cessna 172 with a Lycoming 0320 engine, I'm going to wind up putting it down on a road somewhere. There's so much less redundancy in a simple airplane with a single 4-cylinder engine that, in my mind, that's the airplane that really needs the instrumentation. Because if anything goes wrong with that engine, you're in a world of hurt. If something goes wrong with my engine, all I'm worried about is whether I'm going to max out my American Express card. So the simpler the airplane, the more important it is, in my view, to have good engine instrumentation.
Okay, and Mike would like to know what minimum CHT temp is he looking for before applying takeoff power?
Good question. I actually think there's some guidance for that somewhere, but this is one I can't seem to pull out of a neuron. I'd have to look it up. Basically, we don't want to apply power until the cylinder head temperature is up to some reasonable operating temperature, so that the choke in the cylinder has had a chance to expand out. But to put an actual number on that is a little bit hard. I mean, if I had to pull a number out of the air, I would probably say that I would want to see CHTs up around 200 degrees before I took off. But I believe there's actually some manufacturer's guidance on that, but I'd have to look it up. That's one factoid I just don't seem to have in my memory somewhere.
All right.
Are you shocked?
Yeah, I'm actually. It's pretty rare when you're not able to grasp it, from somewhere in your past.
Yeah.
But Mike,
that's the curse of getting old. I keep burning out these excess neurons and forgetting things.
Well, Mike, another great webinar. We had over 300 people, well over 300 people on tonight.
That's wonderful.
And, want to remind everybody that Mike does a webinar the first Wednesday of every month. And just to clarify, January 4th is the correct date. What is the topic next time?
You were telling me. I think you said it was magnetos.
I believe it is all about magnetos, as I
Yeah.
recall.
By the way, that's a really, really interesting webinar, and since everybody has a magneto on their engine, it will apply to virtually everybody, no matter what you're flying. So I would encourage people to sign up for that one because it's going to be real interesting.
Okay, and it is in fact all about magnetos. I just checked. So, Mike, thanks. Any closing thoughts?
No, I'm just thrilled we had more than 300 people. That's wonderful.
Yeah,
I like the way the needle is moving.
Yeah, I always like a good turnout. Please, anybody who was on tonight, please share with your friends if you enjoyed tonight's presentation. Make sure that they know about the webinar program that we offer. I think it's still pretty much undiscovered country for a lot of people. And please take the survey after you sign off tonight. It's 5 questions. You'll be done in less than 2 minutes. And we really value the input. So, Mike, thank you. Thank everybody else for tuning in. And we will catch you again with Mike January 4th. So good night, everybody.
Good night, everybody.